Good morning, and welcome to today's presentation titled Smart Glass, How Metal Ions Might Revolutionize Tinting and Energy Efficiency. My name is Joe Garcia, and I am the Program Manager for the Energy Innovation and Emerging Technologies program. Today's featured presenter is Mike McGee. Mike McGee is a professor in the Materials Science and Engineering Department and a senior fellow of the Precourt Institute for Energy. His research interests are developing new materials for smart windows and solar cells. He has taught courses on nanotechnology, nanocharacterization, organic semiconductors, polymer science, and solar cells. He received his undergraduate degree in physics from Princeton University and his PhD in material science from the University of California at Santa Barbara, where he did research on polymer lasers in a lab of Nobel laureate Alan Heeger. Now I'd like to turn the floor over to Mike.
Thank you for participating in this webinar. Yeah, today I'm going to tell you about an exciting dynamic window technology that the students and postdocs in my lab have developed. And on this very first slide, you can go ahead and see it. On the left, the window is in its clear state. And then in the next picture to the right, you can see it partially tinting, and you can see a nice neutral gray color. And then if you go over one more, you can see it in a nice black opaque state. And then if you go all the way to the right, you see that the window has switched back to the transparent state. So let me step back and motivate why we would want to have these windows. When I look forward into the future, it's hard for me to believe that we're going to have self-driving cars and yet still be controlling glare by rotating, metal slats, like you can see with the window blinds on the left. And that picture illustrates how sometimes the blinds can get all hung up and not work very well. On the right, you see an example where half of the window is letting too much light in and there's a lot of glare, and then on the other half there is tinting. And it illustrates that really the best way to control glare is not to completely block the light with blinds or curtains, but rather to just attenuate it, more like when you're wearing sunglasses. That way you can still enjoy the view. And we're not just developing dynamic windows because it'll create a more pleasing environment inside all kinds of buildings and cars and airplanes. It's also about saving energy. And this slide has some data that was collected by View Dynamic Glass, and they show that the energy savings you can have with cooling and heating and lighting if you have dynamic windows and they're intelligently controlled such that they're letting in light under certain conditions so that people can use the natural light and use less artificial lighting. And in the winter, the light is coming in to heat the building. But during other conditions in the summer, when that unwanted heat is resulting in the need for air conditioning, then the windows can block it. And the studies show that approximately 20% of the heating and cooling and ventilation and lighting costs can be saved if dynamic windows are properly used. And then in this next slide, you can see something from View Glass's website, and their window is switching between clear and dark. And I won't show their video right now, but there's a web address for it. And you can hear one company explain how their control system would work. And it would have weather data. It would have data from light sensors on top of the building. It would know the layout of the building and where people's desks are, and it would make good decisions on what the tinting of the various windows should be at various points in the day. Now I want to talk about some of the approaches that people are using to control tinting. A lot of people ask me how the windows that I'm going to tell you about later are different from eyeglasses with dynamic tinting. Those have photochromic materials in them, and they darken when they're exposed to UV light. And one thing that's really nice about them, it's all automatic, and there's no need for a power supply. However, some of the downsides, they don't darken in a car because the car windows filter all of the UV light. So you still need sunglasses for driving in a car. And if you don't like the tinting state that arises, there's really nothing you can do about it. If you're outside and you're in a photograph, for example, and you don't want it to the eyeglasses to go dark, you can't override it. And also, let's say you're skiing and it's extremely bright. Photochromics don't have a wide range. They can't go down to, say, 1% transmission. So it would be good to have a technology with more control and a wider range. Another approach are suspended particle devices, and here there are particles sandwiched between a couple of electrodes, and applying a field can line the particles up, and then light can go in between the particles. When there's no field, the particles take more of a random distribution and block more of the light. And this is already being used in the sky roof of some cars, but I've heard various people say that it's too expensive, and others say that it's very hazy. So that brings me to Electrochromics, which is probably the leader for window applications. And in an electrochromic device, there are two transparent electrodes, usually made of indium tin oxide. And on at least one of them, there's an electrochromic material, such as tungsten oxide. And if the voltage is applied in one direction, then the tungsten oxide is reduced, lithium comes into it, and in that state, the material is much darker. Although it's not gray or black, it tends to be somewhat blue. And then on the other electrode, there's some counter material. Sometimes it's electrochromic and it switches color too. Sometimes it's just a transparent material that helps allow the electrochemical reactions to take place on both sides. Tungsten oxide is typically sputtered, and in these devices, both of the transparent electrodes, the electrochromic, the electrolyte, and the counter material, they're all sputtered, so there can be a couple microns of material. And that means that you need a long line of sputter tools or have a lower throughput on a smaller system. So it is somewhat expensive. Another problem is that sometimes there are pinholes, in other words, regions missing the material, and so those spots don't switch color. And so typically the yield is only about 1/3, and that means that 2/3 of the windows are having to be thrown out. And I think those are the primary reasons why this technology is at about $50 per square foot. And I've heard from people in the industry that $20 to $30 per square foot is probably where the technology would be much more widely adopted than it currently is. There is a lot of excitement for this technology, and I think there's a lot of sense that something big is about to happen right around the corner. And companies like Canestral and View and Sage, they don't usually reveal exactly what they're making, but it's probably tungsten oxide or some similar metal oxide. And you can see Canestral has raised 100 million, View has raised at least 650 million, and Sage Glass was acquired by Saint-Gobain. And then there are other smaller companies as well that are working on innovative dynamic glass technologies. Probably the most commercially successful electrochromic company is Gentex, and they use a molecule, methyl viologen, that switches colors when it's oxidized and reduced. And they chose an application that's an easier one than Windows. They make the Rearview mirrors for cars that have a light sensor. And if someone is driving behind the car and the high beams are in the mirror, it'll sense that and darken the window, as you can see in the slide there. And so they have about $1.5 billion per year sales for that product. They also make the windows for the Boeing 787 Dreamliner. And here you can see one of their photographs, and on the left you have a completely clear window, and then it's getting darker as it goes over to the right. I took some photographs myself when I was in a Dreamliner recently, and I spent a good chunk of the flight observing how people were using the windows, and asking people how they liked it. And generally, people, they do like it. They like the fact that when the window is darkened, you can still see what's outside. You don't completely lose the view. The pilot loves it because they can make all the windows go clear before landing, which is a requirement. But you also see that because the window switches over a period of minutes, and a lot of people don't think it's working when they push the button, and so they keep pushing the button over and over. You also see that it's not currently dark enough for a lot of people if they're trying to sleep. And it's very bluish. In fact, in the next slide, you can see my hand when the window is in the clear state, and then my hand when it's in the dark state. And you can see that it's a very blue window. And you can imagine, particularly in homes and restaurants and office buildings, people wouldn't want to have that blue color, and they wouldn't like the way it makes other people appear. So it's clearly important to make the windows switch faster, to have them go darker, and to have a more neutral color. I have read an article just in the last few weeks that Gentex is releasing a next generation of the window that is supposed to be better, but I haven't seen that, and I don't know what they did to improve that window. So just to highlight some of the needs here for Windows technology, it needs to have uniform switching. And I should elaborate that a lot of the technologies, they work well when they're small, but it's hard to make a large window switch fast. And the reason is that when the window's large, it's drawing a large amount of current. And that when that current goes through the transparent electrode, there's a voltage drop just due to Ohm's law. And then, the switching depends on the voltage. And so the windows switch faster on the edges where the voltage is high, and slower in the center. And that leads to an effect called irising. So probably better electrodes are needed, or windows that switch with a lower current. And then I've highlighted very high contrast is needed, particularly if privacy is needed, say in a situation, a residential situation. You have to go below 0.1% transmission to create a state where people outside can't see in. And then, of course, the windows need to be durable. They should be stable in the resting state, meaning that if you turn it dark, it will stay dark, preferably without having to continue to apply power. And then it's very important that the windows have very low haze, in other words, that they not scatter light. So with all that in mind, we wanted to take a completely different approach. We're not completely convinced that the leading technologies out there will ever have all of the properties that are needed for the most demanding applications, like windows in homes and commercial buildings. And we thought of a totally different way, that is to use metal instead of metal oxides. It only takes about 20 to 30 nanometers of metal to completely block light. You don't need microns, just 20 to 30 nanometers. And also, metals are very durable. And the challenge in this application is that and for most of the situations, the materials are exposed to full sunlight and a wide range of temperatures. But metals, can handle that without any trouble. And then in the approach I'm about to show you, we're going to have a transparent electrode, and then we're going to have just a metal grid for the other electrode, and then we're just going to inject an electrolyte liquid in between, and that can be done quickly and very inexpensively compared to sputtering a couple of microns of material. So yeah, this next slide just shows what we're doing. We're gonna plate metal when we want the window to darken, and then we're just going to strip it when we want it to go clear. We're really just moving metal from a transparent conducting oxide over to just a metal grid counter electrode. The postdoc in my group, Chris Barile, thought carefully about what metals should be used, and he created this table. And down at the bottom of the table are some candidate materials that would be inexpensive, but these materials are hard to plate, and it would be very difficult to reversibly plate them, because they're very prone to oxidation, and once they oxidize, then it's hard to strip them. If we go up to the top, things like gold, platinum, palladium, they're very resistant to oxidizing. However, perhaps for the same reason, they're very expensive metals. So in between are some attractive candidates: silver, copper, bismuth, lead. And we found that they work very well. We started with copper because it's well known that copper can be electroplated, and there's a lot of literature on how to do it. But copper by itself is red, so we needed to put another metal in there to get a neutral color. We started with lead because there's so much known about the electrochemistry of lead since it's used in lead-acid batteries. And we made great windows, but the early feedback we got is that it was a non-starter to have lead in these windows. So we moved on to silver, and we're also able to make nice windows with that, and that's what's reported in our manuscript in the journal Joule. So I'll tell you a little bit about how we got this working. Our first attempts were on bare indium tin oxide, and we had some success, but it didn't work as well as we would have liked. Here you can see scanning electron microscope images, and you see that there are certain, just particles of the metals plating, and it's not plating uniformly everywhere, and light is able to go in between the particles. And even worse than that, when we cycled it 1,000 times and looked at the morphology with SEM, we found that the morphology was changing a lot. And we're reasonably sure that that happens because we don't think we're able to completely strip the metal off of the indium tin oxide, and the residual metal influences the future growth. Here you can see when we were doing a cycling experiment where we would plate for 60 seconds and then strip for 60 seconds, the minimum transmission was getting worse and worse over time. And then Chris decided that the problem was that only some sites on the ITO are good for plating metal. And so he attached platinum nanoparticles to the surface, knowing that metal will plate more easily on platinum than it will on ITO. And that worked really well. We don't have a continuous thin film of metal. We're still getting nanoparticles of metal, but you can see in these SEM images that there's a pretty good distribution. All patches on the window have a fairly similar morphology. And we found that when we cycled it 1,000 times, we didn't get significant changes in the morphology. We believe that in the strip cycle, all of the metal comes off, and we're then starting over again with a clean platinum surface. And with that, when we cycled it back and forth, we got consistent results over 1,000 cycles, and I'll show even more cycles, later on in this presentation. Here we're cycling between 90 and 40% transmission. We could go deeper. We just we're using a less aggressive cycling, and we're just doing a short switch there to do 1,000 cycles relatively quickly. This next slide shows just how low the transmission can go. You see here that after a few minutes, the transmission is well below 1%. And a lot of people ask what the switch time is, and that just depends on how dark someone wants the window to go. And just say 10 seconds, it's already down around 30%, which is clearly darkened. But it takes a few minutes to plate enough metal to go below 1%. And this slide does illustrate that this technology has a very wide range, because we can just keep plating metal. We can make the windows go as dark as anyone wants them to go. This next slide shows the spectrum. You've already seen pictures, so you can see that these things do look black. And here's just quantitative data showing how the spectrum is going down with time. It also shows that this just keeps going into the infrared, and I'm not showing it here, but the attenuation goes out well past 2,000 nanometers, which is as far as we've measured it. And of course that makes complete sense. This is metal, and metal is very effective at blocking light over an extremely wide spectral range. And then you can see the spectrum just return to its normal state if we reverse the voltage. On the right, you see 2 days worth of data. So first the device is put in its opaque state, and then the power is removed, and you can see the metal stays put. And so with no power consumption, the window stays in its dark state. And then at the 24-hour mark, metal is stripped, and then again the power is taken away, and it'll stay in its transparent state. So this technology consumes very little power, just uses a small amount of power during the switch, and that's it. Here you can see all the steps we use to make a window. We start with a piece of glass that you can see in the first box, and then we put a butyl rubber edge seal around there. It's probably not optimized yet, but it's something we just happen to have in our lab for packaging solar cells. And then we put copper tape around there, and that's going to be the counter electrode. For a window this size, we don't need a fine grid of copper throughout the window. And then we're putting on some more rubber edge seal over that. Then we have a second piece of glass that has the ITO on it, and it has copper tape around the edges to help spread the current. So we'll be bringing current in from all around the edge of the device. And in step 5 here, we've sandwiched all of that together. And then we're putting it on a hot plate at 120 degrees C. We put some weight on top of that, and that presses the two pieces of glass together, and the rubber is a little bit softened up, and we get a nice seal between the two pieces of glass. And then coming over into step 9, we have the electrolyte solution. There's some polymer in there, hydroxyl oxycellulose, which is also used in hair gel. And it's got the metal ions in there. And with one syringe and needle, we inject that. And then there's another needle to help remove air from the other side. And that gives us a complete window. This slide takes a more detailed look at some of the optics. You can see the transmission in the clear and the dark state, and in the clear state, it is clear in the visible, but the ITO is absorbing out in the infrared. And then we see that there's not a whole lot of reflection off of the device, maybe 10 to 20%. Most of the impact of plating metal is in the absorption, and we see here we're getting about 80% absorption across most of the film. And I don't think we understand that in full detail yet. But having this nanostructured metal is causing the light to get very heavily scattered, and then we're probably exciting a lot of plasmonic resonances in the nanoparticles that's leading to strong absorption. But yeah, there is some debate. Some think it would be great to reflect the light, and that would keep the window cool, and it would just reject the heat. But a lot of people we've talked to actually prefer the absorption and the black color, and point out that you really don't want your window to look like a mirror. And there are even laws in Singapore, for example, saying that the windows cannot reflect more than 30%. Because then you can just send light over to other buildings. And also, if there's a little bit of curvature in the window, you can have a light focusing effect, and certain spots can get very hot. So for a lot of the applications, it's probably very good that these films are absorptive and black. I think it's also worth explaining that these films do not obey Beer's law. I'll admit, when we designed the project, that was the plan. But the transmission does not drop exponentially with film thickness. And that is because we don't have metal everywhere. And so more light gets through than you would expect from Beer's law, because light is going in between the particles. And there's some, I think, good and bad news associated with that. Probably the good side of it is that our transmission versus deposition curve isn't quite as steep as the Beer's law curve. And that means that we can have just slight variations in film thickness and not have a huge variation in transmission. But I will say we're going to at least try to have the metal plate everywhere, because if it does, and we get to the Beer's law curve, then we will get low transmissions with less metal, and that will mean with less current, and that'll mean that we can switch the window faster. And here's data for a window with a copper silver gel electrolyte. We cycled it 5,500 times, and then at that point decided that we needed to use our two potentiostats for other experiments. But it was very exciting that we didn't see degradation due to cycling after that many cycles. So just to review some of the highlights here, I think a key advantage that we have with reversible metal electrodeposition compared to electrochromics based on transition metal oxide is the gray color in the partially tinting state, and the black color when it's highly opaque. Right now, I think our switching speeds are comparable. People who've read our paper are excited about the fast switch, but to be fair to the competition, if we made meter by meter windows, we would have to run them slower as well to prevent the irising. However, I'm optimistic that we can improve the metal morphology and get to a switch situation where we do switch 2 to 5 times faster for a window of the same size. I think it would be premature for me to put out a number on cost, particularly as a professor who's never run a factory. But if I just compare this directly to the Electrochromics, I think it's very promising that it can be cheaper. We'll have less material that is sputtered in a vacuum chamber, and so I think there's good potential to reduce cost. And then a last advantage is the very high range of transmission, and that we can go dark enough to have privacy. So when we look forward to our challenges, it would be really wonderful if a large window could switch rapidly. We've been told that it's not necessarily a requirement for architectural applications, that certainly a smart control system knows what the sun is going to do and can start darkening the window before the glare gets too bad. But we hear other people say, and especially those who want to put this in automobile car roofs, that you really want a fast switch. When people press a button, they want to see something happen right away. Otherwise, they might think it's broken. So if the improvement here, it might be in having the metal more effectively block light so that we can use less of it. But it's probably more in making a better electrode. And we've got some ideas for incorporating metal grid lines into the electrodes so that we can pass more current without a voltage drop. And then, of course, long-term stability is going to be crucial. And, we have to make sure not only that we can cycle it, but it has to handle ultraviolet light. We can't have the polymer gel break down in the UV light. We have to make sure that it can handle an elevated temperature for a long time. We are seeing some issues with the indium tin oxide being etched, and we're moving towards more stable electrodes for that. And finally, I'd like to thank a really outstanding team. Chris Barile was the postdoc who developed all of the chemistry for this project, and he's now a professor at the University of Nevada at Reno. And Dan has interacted with a lot of the companies as part of a class he took on entrepreneurship, and learned a lot about what the needs are for dynamic windows, and did a lot of the work in the optics and building the package. And Tyler and Michael and Teresa are developing some even better chemistries that I haven't shown you yet, but you will see some even better windows down the future. And then finally, I really want to thank the Stanford Precourt Institute for Energy for giving us a seed grant to get this going. This was a completely new area for our group, and it was great to have someone give us this chance to try something new. And I thank you all for your attention, and I hope you enjoyed this presentation.
Thank you again for joining us for the presentation today. Just a reminder that this presentation is sponsored by the Energy Innovation and Emerging Technologies program. Please visit energyinnovation.stanford.edu if you'd like to learn more about this type of technology, as well as some of the courses we have to offer, such as solar cells, which is related to generating electricity in residential, commercial, utility, and off-grid sectors. Once again, please visit energyinnovation.stanford.edu.